The SI system is a system used to describe the quantity of a substance. You have 7 base or fundamental units. For length, you have the meter, time is measured in seconds, mole is the amount of substance you have, the mass is in kilograms, luminosity is in candelas, current is measured in amperes, and temperature is measured in Kelvin. Here are the prefixes you have to describe how many units you have of a substance. For example, if you have 1 terasecond, it would be 1 second times 10 to the 12. In dimensional analysis, all measured quantities consist of a number and a unit. By including units in calculations, you can apply the same arithmetic operations used with quantities and numbers to units. That means for a unit you can multiply them, you can divide them, and you can cancel them out. In the example of area, you have area, you're looking for feet squared. You have a length of 4 feet and a width of 3 feet. So you would have 4 times 3 is 12. Feet times feet is feet squared. Your area would be 12 feet squared. When naming compounds, you want to start by knowing 2 sets of rules, ionic and covalent. For ionic bonds, you want to start by naming the metal, followed by its charge if it has multiple charges, then the nonmetal with the suffix "ide." For example, with calcium and oxygen, you form calcium oxide. Calcium always has a charge of +2, so it won't need to be included. For polyatomic ions, you have the metal, followed by its charge if it has multiple charges, and then stating the polyatomic ion. For FeSO4, you have iron with a charge of 2, sulfate. For covalently bonded compounds, you want to use the prefixes for both the first nonmetal and the second nonmetal, provided that the first is not 1. For example, with water, you have hydrogen 2 oxide, so you have dihydrogen monoxide.
Mass percent can be defined as the mass of element X divided by the total mass of the compound times 100. And a mole can be defined as the SI unit of the substance, or take 6.022 times 10 to the 23 entities of anything. For example, a mole of nitrogen would be 6.022 times 10 to the 23 entities of nitrogen, and all that mass with all those entities would be its molar mass. Now we can find the mass percent of nitrogen and hydrogen in tetrazine, which is 4 atoms of nitrogen times the atomic mass divided by the total molar mass of this compound, which gives us 93.27% mass of nitrogen. Similarly, to find the mass percent of hydrogen, it would be 4 atoms of hydrogen times the atomic mass divided by the molar mass, which will give us 6.73% hydrogen. Now we can take these percentages and find the mass of nitrogen and hydrogen in 456 grams. All we have to do is multiply the percent of mass of nitrogen and hydrogen in any compound of tetrazine to find the total mass. It would be 456 times 93.27 would give us 425.31 grams of nitrogen. And similarly, 106.73 times 456 would give us 30.69 grams of hydrogen in this compound of tetrazine.
Hi, so an acid is a substance that has a hydrogen atom in its structure, and a base is a substance that has a hydroxide or an O2 negative atom in its structure. When they combine in an acid-base reaction, the acid will donate its hydrogen proton over to the base's hydroxide anion to form H2O liquid water. Seen better yet in the net ionic equation, we see the hydrogen being transferred over to the hydroxide anion, and they then combine to form H2O liquid water, and also a salt, sodium chloride. Now, a strong acid and base dissociate completely in water to form a strong electric current, while a weak acid and base do not dissociate completely in water and form a weak electric current. Seen before me are nitric acid and sodium bicarbonate, lemon juice, and baking soda. When the acid and the base will combine to form CO2 gas and liquid water. Seen here, the acid donates hydrogen proton over to the base's hydrogen bicarbonate anion to form H2CO3. This then will decompose into liquid water and CO2 gas, forming our total ionic equation here. In our net ionic equation, you see the proton transfer of the acid donating its hydrogen proton over to the base's sodium hydrogen bicarbonate to form H2O liquid water and CO2 gas, as seen here in our experiment. You hear that? That's CO2 gas forming and liquid water. And that right there is an acid-base reaction.
When speaking about the energy of a chemical reaction, energy is always transferred into and out of the reactants, which are referred to as the system, and the space around it, including the air, reaction vessel or surface, or anything that can absorb or emit any radiation are considered part of the surroundings. Endothermic and exothermic reactions specifically deal with the heat energy that is transferred during the reaction. An endothermic reaction is one where the total heat energy of the surroundings and system is lower than before the reaction occurred. In this case, the heat energy is absorbed, converted, and used to create new chemical bonds. Even though the reaction absorbed the heat energy, it doesn't mean that it gets hot. Because the heat energy is converted instead of held as heat energy, the product and surroundings will actually have less heat energy and therefore be cooler in temperature. Exothermic reactions are similar to endothermic reactions, but instead are where the total heat energy of the system and surroundings after the reaction are higher than before. This is observed when the system is at a higher temperature after the reaction. To be clear, not all energy transferring in and out of a reaction is heat or thermal energy. It can sometimes be mechanical or radiation, but these aren't accounted for when talking about endo and exothermic processes. Effusion and diffusion are two behaviors that gases have when transferring from one medium to another. The main difference is that effusion is the movement of gas from a pressurized volume into a vacuum, while diffusion is the transfer and mixture of gas molecules from one pressurized volume into another, usually with a different gas mixture. Here, in the ideal process of effusion, there would be a vessel with a known pressure of gas molecules connected to an evacuated vessel with a valve and a flow meter. When the valve is open, we can measure the rate that the gas moves into the evacuated volume and use Graham's law to determine the molar mass. Similar to effusion, the ideal diffusion scenario would have two pressure vessels connected with a valve, but this time both vessels are pressurized with two different gas mixtures. When the valve is open, the gases from both vessels will disperse into each other's vessel until the mixture of them is even throughout both. To calculate the diffusion of one molecule relative to another, we can use this derivative of Graham's law, otherwise known as Graham's law of diffusion.
Electron orbital is a visualization of a math function called Schrodinger's equation. This right here is a wave function. Squaring this yields the probability of finding an electron within a region of the atom, also known as an electron orbital. Now imagine we have a hydrogen atom. Our nucleus is here. An orbital is really a region of higher probability of where an electron can be found, which can be here, 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 or anywhere inside these bounds. Now, as you see, this is a sphere, but not all orbitals are spheres. We really need three quantum numbers in order to distinguish orbitals from each other from the various shapes and energy levels. We have n, which is the relative distance of an orbital from its nucleus. We have L, which is the relative shape of an orbital. And we have M sub L, which is the orientation of an orbital from its nucleus. Now, when you combine these quantum numbers, you can begin to form assigned name designations and assign name designations and distinguish the energy level of a certain orbital. For example, we have the 2s2 orbital. Right here, n is equal to 2. S, and this orbital is within the s sublevel, or L is equal to 0, and it has 2 electrons within this orbital, since every orbital can hold a maximum of 2 electrons. Thanks for watching.
Discussing trends in a periodic table, there are 3 to know. Ionization energy, which is the energy required to remove the outermost electrons. Electron affinity, the energy required to add an electron to the outermost shell. And the atomic mass of the element. On a periodic table, ionization energy will tend to increase as you go up a group and across a period. Electron affinity will also tend to increase as you go up a group and across a period. Atomic mass, however, decreases as you go across a period because you're adding outer electrons and protons, but will also increase as you go down a group because you're adding inner electrons.
Chemical bonding occurs in 3 ways: metal and metal, metal and nonmetal, and nonmetal and nonmetal. This bonding is also dependent upon several different properties specific to each element, including atomic size, ionization energy, electron affinity, and effective nuclear charge. When it comes to a metal forming a bond with a nonmetal, it is considered ionic and a transfer of electrons. It occurs between elements that typically have large differences in their tendencies to gain or lose electrons, which will give the compound a noble gas configuration. Due to the electron transfer, the atom is left with a positive or negative charge that attracts the opposite of like compounds, creating what is known as an ionic solid. As far as 2 nonmetals bonding, they tend to share electrons rather than a full transfer to create a noble gas configuration, which is called a covalent bond. Based on high ionization energies and highly negative electron affinities, atoms' nuclei attract the valence electrons from other atoms, creating a localized bond. The last type of bonding is metal with metal, known as metallic bonding. Metals share their electrons in a different type of way than nonmetals because of their larger atomic size and lower ionization energies. They pool electrons in a sort of sea of electrons which just flows between the atoms. In summary, the different atomic properties of elements determine their bonding type and structure. When several atoms bond together, they begin to form certain geometric patterns. These patterns depend on the number of shared and lone electrons. The linear molecular shape is when two atoms bond to a central atom and have a bond angle of 180 degrees. This geometry is also considered nonpolar. For a trigonal planar molecular shape, you have three atoms bonded to a central atom and no lone pairs, making a bond angle of 120 degrees. This geometry is considered nonpolar. Tetrahedral geometry occurs when there are four bonding pairs of electrons on the central atom and no lone pairs. This geometry is considered nonpolar. In a trigonal pyramidal arrangement, there are three bonding pairs on the central atom and one lone pair of electrons. This lone pair repulsion pushes the other atoms down to form this geometry. For a bent molecular shape, a central atom has two bonding pairs and two pairs of lone electrons. These lone electrons have less restriction and therefore give greater repulsion, creating smaller bonding angles than the all-bonding pair version. This geometry is considered polar because it has unequal poles and dipoles. For a trigonal bipyramidal molecular shape to occur, there needs to be 5 identical bonding pairs of electrons on the central atom. This is an example of nonpolar geometry. Similar to the trigonal bipyramidal, a seesaw shape will have 4 bonding pairs of electrons and 1 lone pair of electrons. This is a polar arrangement. With a T-shaped molecular shape, there are 3 bonding pairs of electrons on the central atom and 2 lone pairs of electrons as well. This is an example of a polar geometry. Octahedral molecular geometry forms when there are 6 bonding pairs of electrons on the central atom with no lone pairs. This is a nonpolar arrangement. The square pyramidal molecular geometry has 5 bonding pairs of electrons on the central atom along with 1 lone pair of electrons. This is a polar molecular shape. The square planar molecular shape has 4 bonding pairs of electrons, but also 2 lone pairs of electrons on the central atom. This is an example of a nonpolar molecular shape. In conclusion, you can easily identify a molecule's geometric arrangements by its bonding pairs of electrons and lone pair of electrons. These shapes can also determine polarity of a molecule based on its symmetry.
sp hybridization can explain the linear structure in molecules. In it, the 2s orbital and one of the 2p orbitals hybridizes to form 2 sp orbitals, each consisting of 50% s and 50% p character. sp2 hybridization can explain the trigonal planar structure of molecules. In it, the 2s orbital and 2 of the 2p orbitals hybridize to form 3 sp orbitals, each consisting of 67% p and 33% s character. sp3 hybridization can explain the tetrahedral structure of molecules. The 2s orbital is mixed with all 3 of the 2p orbitals, creating 4 hybridized sp3 orbitals. Each of these has 25% s and 75% p character. sp3d hybridization can explain the trigonal bipyramidal structure of molecules. The 3s orbital, 3 3p orbitals, and 5 3d orbitals create 5 hybridized sp3d orbitals. sp3d2 hybridization can explain the octahedron structure of molecules. One 3s orbital is mixed with 3 3p and 2 3d orbitals to create a hybridized sp3d2 orbital.